Namaskar. I welcome you in this today's session. Today we are going to discuss Langmuir Adsorption Isotherm. So this isotherm was proposed by Irving Langmuir in 1916. In previous session we have seen what is meant by adsorption isotherm and adsorption isobar. Okay, so adsorption isotherm is nothing but it is the plot of, or it is a relationship between amount of substance adsorbed on the adsorbent, or we call this as extent of adsorption, and equilibrium pressure or equilibrium concentration at constant temperature. So in previous lecture we have seen the Freundlich adsorption isotherm, and in this session we are going to see the Langmuir adsorption isotherm. So let us discuss. So in this session we are going to derive this equation. This is the Langmuir adsorption isotherm equation, where x by m is equal to ap upon 1 plus bp. Okay, and this is the plot which we are going to see in detail. So on this y-axis we are plotting the ratio of pressure and extent of adsorption, with on on x-axis we are plotting the pressure, and this is the nature of the curve. We will see in detail. Now let us discuss the assumptions of Langmuir adsorption isotherm. First assumption is that the surface of a solid is made up of elementary spaces called as adsorption sites. All the adsorption sites are uniform and have affinity for gas molecule. Okay, for example, look at this is the adsorption surface, and these adsorption surface have a unique same elementary spaces, and these spaces we call this as the adsorption sites. Okay, on these adsorption sites our gas molecule undergoes condensation or adsorption. Second assumption, each adsorption site adsorb one gas molecule and there is a monolayer adsorption. Okay, means these adsorption site, each site will adsorb only one gas molecule. Okay, so for example, look at here. So each site there is occupation of only one gas molecule. The second half part of this second assumption is that there is a monolayer adsorption. Monolayer, only one molecule is adsorbed by each adsorption sites. Mono means one. Okay, mono, one or single layer. Third assumption, there is no interaction between adsorb gas molecule. Okay, there is no interaction means there is no physical or chemical kind of interaction between this adsorb gas molecule among themselves. Fourth assumption is at the equilibrium, the rate of condensation, we call this as adsorption, and the rate of evaporation, that is desorption, are the same. Okay, just as we have seen, the condensation means, okay, it is called as the adsorption. Okay, adsorption of adsorbate, that is gaseous molecule, on the surface of adsorbent is called as the adsorption, and this process is called as the condensation. Okay, a reverse of this is called as the desorption, such as, okay, here you can observe that the gas molecule are getting detached from the adsorption sites. Gas molecule are getting detached from adsorb site, and here the gas molecule are getting adsorbed on the adsorption side. So reverse of adsorption is called as the desorptions, or reverse of condensation is called as the evaporations. Now let us derive the equation for Langmuir adsorption isotherm. So look at the diagram. Here we have the adsorbent. Adsorbent means it is the substance over which adsorption takes place. Now let us assume that our adsorbate or gaseous molecules gets adsorbed on some part of these adsorbents. Okay, and they occupy the fraction theta. Okay, this is occupied fraction means this is the fraction occupied by adsorbed molecule theta, and so this remaining part will be, it will be equal to 1 minus theta, and this 1 minus theta will be unoccupied fraction of the adsorbent. Theta is the occupied fraction of the adsorbent. So suppose at any instant of time fraction theta of the adsorbent surface is occupied by adsorbate. Then the 1 minus theta means here this portion, remaining portion other than this blue dot. Okay. Then 1 minus theta will be unoccupied fraction of the adsorbent surface. Now, according to the kinetic theory of gas, at constant temperature, the number of gas molecule which strike to the adsorbent surface means, okay, for example, okay, this is the adsorbent surface and this gas molecule are striking. So number of gas molecule which strike to the adsorbent surface, that is the rate of condensation or the rate of adsorption, is directly proportional to the pressure of gas. More the pressure, more speed the gas molecule will have. Okay, with the more speed they will strike on the gaseous surface, sorry, on the adsorbent surface. So we can say that the rate of condensation or rate of adsorption is directly proportional to the pressure into unoccupied fraction of the adsorbent 1 minus theta. Okay, here आता गॅसियस मॉलिक्यूल ऍडझॉर्बंट मॉलिक्यूल कुठे स्ट्राईक करतील, जिथे त्यांना एम्प्टी स्पेस मिळेल त्याच ठिकाणी ते स्ट्राईक करतील. ओके, नाव इफ वी सॉल्व दिस प्रोपोर्शनॅलिटी कॉन्स्टंट, okay, alpha, then we get rate of condensation is equal to k1 into p into 1 minus theta, where k1 is called as the proportionality constant. K1 is called as the proportionality constant. Now the rate at which gas molecules, that is adsorbate, evaporates, that is desorption from the surface, will be directly proportional to the occupied fractions by the adsorbate. Okay, therefore rate of evaporation or rate of desorption will be, okay, this is the process of rate of desorption or the rate of evaporation. Detachment of adsorbate from surface of adsorbent is called as the evaporation. Okay, and हे इव्हॅपोरेशन किती असेल, जेवढ्या गॅस मॉलिक्युलनी ऍडझॉर्बंटचा सरफेस ऑक्युपाय केला आहे तेवढंच तो काय असणार आहे, इव्हॅपोरेशनचा रेट असणार आहे. सो द रेट ऑफ इव्हॅपोरेशन विल बी इक्वल टू द ऑक्युपाइड फ्रॅक्शन्स. सो therefore the rate of evaporation is directly proportional to the theta. Simplify this proportionality, then we get rate of evaporation is equal to k2 into theta. Let us say this is the equation number 2 and k2 is called as proportionality constant. Now at equilibrium, what will happen? At equilibrium, this rate of evaporation will be equal to rate of condensation. So from equation 2, okay, it is k2 theta, and from equation 1 just we have seen it is equal to k1 times p into 1 minus theta. So let us simplify this equation, then we get, therefore k2 theta equal to k1p minus k1p theta. Okay, now take this term to the left hand side, then we get, therefore k2 theta plus k1p theta is equal to k1p. Okay, so next step will be, okay, take theta common from this equation, then we get k2 plus k1p, okay, in bracket theta, which is equal to k1 times p. Okay, now adjust the equation for theta, take this term to the right hand side, then we get theta is equal to k1 upon p, k1 into p upon k2 plus k1p. This is equation number 3. Okay, now the amount of gas adsorbed per unit mass of the adsorbent, that is x by m. X stands for amount of the adsorbate and m stands for the amount of adsorbent. So the amount of gas adsorbed per unit mass of the adsorbent is directly proportional to the occupied fraction of the adsorbent. So therefore x by m is directly proportional to the theta. So it is equal to, if we solve this proportionality constant, then we get k times theta. Now theta, just we have derived the equation. Okay, theta means theta is equal to k1 times p upon k2 plus k1p. Let us put this value of theta in this equation. Okay, then we get, therefore x by m equal to k times k1 into p upon k2 plus k1p. I have just put the value of theta which we have derived just now into this equation. Okay, and we get this. Now let us simplify this equation. Okay, so we get K into K1 upon P, K2 plus K1 into P. Now divide numerator and denominator by K2. Okay, we will divide both this numerator term and denominator term by K2. Then simplify this, then we get K into K1 upon K2 plus, okay, K2 upon K1, K2 is equal to 1 plus K1 upon K2 here into P. So we will replace this term by A and B. Therefore, we get X upon M equal to AP upon 1 plus BP, where A is equal to K upon K into K1 upon K2, and B is equal to K1 upon K2. So this equation 4 is known as Langmuir adsorption isotherm. Equation 4 is known as Langmuir adsorption isotherm. Now let us plot this Langmuir adsorption isotherm, that is application of Langmuir adsorption isotherm. So this is the equation just we have derived. Now divide both sides of above equation by pressure term, and then we get, okay, therefore P upon X upon M is equal to this BP plus 1 raised upon P, AP upon P. Simplify this equation, then we get, okay, here BA upon P plus 1 upon A, and this equation is similar to Y equal to XM into, sorry, plus C. Here X is equal to P and M is equal to slope, that is B upon A. If we plot this Y term P upon X upon M versus pressure, then we get this kind of curve. Okay, so on y-axis we have plotted pressure upon extent of adsorption, and on x-axis we have plotted the pressure. So we get a straight line like this. Okay, now this y-intercept is equal to 1 upon A. Okay, and reciprocal of intercept, we will get the value of A, that is the Langmuir adsorption constant, and the slope of the straight line will give us the value of B upon A. So we have derived this equation X upon M is equal to AP upon 1 plus BP. This is the Langmuir adsorption isotherm, and this is the plot just we have derived. So Langmuir adsorption isotherm is nothing but the relationship between extent of adsorption and the equilibrium pressure at constant temperature. So thank you for watching these sessions. If you like this video, okay, then subscribe this channel so that you will get further notification of videos. So thank you for watching.